Hi, I'm Alan Perry, and welcome to Scholar Sauce. Welcome to part 2 of our exploration of Euclid's fifth postulate. In part 1 of this video, we found an old box in my garage full of Euclidean geometry. We discussed how Euclid was the first to attempt to construct the geometry of the plane from a set of first principles called axioms, and we learned that many mathematicians wondered if the fifth postulate, which was much more complicated than the first four, could be proved just using those first four axioms. To help our discussion out, we modernized the question a little, gaining a more modern treatment of Euclid's first four axioms in what's called neutral geometry, and finding that the question of whether we could prove Euclid's fifth postulate came down to a question of proving or disproving each of three possible parallel postulates, where for each line L and a point P off the line, there's either no lines through P parallel to L, one parallel line, or at least two parallel lines. And it turns out that we can make some decent progress on that question. It's not too complicated to prove in neutral geometry that given a line and a point off the line, there has to be at least one parallel line. And this immediately shows that the elliptic parallel postulate is not true under these six axioms, and that any hybrid version of multiple postulates can't contain any place where there are no parallel lines. And for a while, that's where mathematicians were stuck, but they made some additional progress in another area. Within the framework of neutral geometry, mathematicians began to find a lot of statements that were logically equivalent to the Euclidean parallel postulate. Logically equivalent means that either statement implies the other. Thus, if you could prove any of these logically equivalent statements, you would get the Euclidean parallel postulate for free. And there were several that seemed like low-hanging fruit. For example, the following facts are all logically equivalent to the Euclidean parallel postulate within the framework of neutral geometry. The first, of course, Euclid's fifth postulate. 2, the sum of the angle measures of any triangle is 180 degrees. 3, the sum of the angle measures of any convex quadrilateral is 360 degrees. And then 4, my personal favorite, there exists a rectangle is equivalent to the Euclidean parallel postulate. That's right, if you can show that it is guaranteed to be possible to draw a rectangle in neutral geometry, then you've proven that Euclid's fifth postulate follows from the first four. Just an easy rectangle. That can't possibly be that hard, right? Right? Well, several mathematicians attempted to create a rectangle, and they got close. Two such quadrilaterals that can always be formed in neutral geometry are known as Lambert quadrilaterals and Sacchetti quadrilaterals. These quadrilaterals got their names from a pair of 18th century mathematicians, Johann Lambert and Giovanni Sacchetti. To see why these can be formed in neutral geometry, we note a theorem that can be proven in the neutral geometry framework. This says that no matter what line and point we pick, there is a line through that point that is perpendicular to the original line. Aren't perpendicular lines great? Meh, they're all right. What? You're the one who keeps setting them up. Anyway, note here two limitations to what this theorem says. If the point P is on the line L, then we have no knowledge over where the line N goes or what line it intersects. We only have information on what angle it makes with L. That is, when we create a perpendicular line this way, we can't choose what it does once it leaves L. If the point P is not on the line L, then while the line M will intersect the line L at some point Q, sometimes called the foot of the perpendicular, and will make a right angle there, we have no information about where on the line L that point Q is. That is, when we create a perpendicular line this way, we can't choose where it lands on L. Now let's actually try to draw a rectangle. It shouldn't be too hard. Remember though, we can only use things that are guaranteed by the neutral geometry axioms. First, we know that rectangles have congruent opposite sides. So let's try to take advantage of that. Let's pick 2 points, A and B, and draw the line segment AB between them. We can do that by the incidence postulate. Now let's use the theorem we just mentioned to raise lines perpendicular to AB at both points A and B. Now pick points C and D on these perpendicular lines on the same side of the line AB, such that the distance from A to D is equal to the distance from B to C. This can be done by the ruler postulate. Now draw a line segment between C and D, again using the incidence postulate. Now we have a quadrilateral ABCD with 2 right angles for base angles and 2 congruent opposite sides. This is called a Sacchetti quadrilateral. You might think initially that this has to be a rectangle, but note that we don't know whether the line between C and D is perpendicular to either side. In fact, the best that neutral geometry is able to prove here is that the top or summit angles are congruent and that they cannot be obtuse. That is, they are either acute or right. Now we want to eliminate the acute case, but no matter how many emergency rooms we take this to...
Do you want an acute case on your hands?
Sorry. I mean, no matter how many theorems we try to use, nothing seems to work. You might try to show then that the length DC is equal to the length AB and try to get a rectangle that way. But there you'll run into trouble too. Here, the best that neutral geometry can do is prove that DC is greater than the MCU.
Oh, snap. You're totally right.
I mean that the length DC is greater than or equal to the length AB. Give it a try. If you find that you can eliminate the acute case or show that the length DC is equal to AB, then you either did something incorrectly or you used a statement that is equivalent to Euclid's fifth postulate, which would defeat the entire point of trying to create a rectangle to prove Euclid's fifth postulate. You can't use the thing that you're trying to prove as part of your proof. We call that circular logic, and we're talking about rectangles, dang it! Sorry. Anyway, that's not very satisfying. I mean, sheesh, rectangles can't be that hard to draw, can they? All right, let's try again.
Let's try this one more time, but
this time let's start with a line L and a point on that line P. Use our perpendicular line theorem to find the line M through P that's perpendicular to L. Pick a point Q on L and a point R on M different from P. This can be done because of the ruler postulate. Then pick a fourth point S in the interior of the angle QPR. This can be done because of the plane separation postulate. Use our theorem again to drop a perpendicular from S to L with foot T and a perpendicular from S to M with foot U. Note that we don't know whether T is Q or U is R or not, since we can't control where these perpendiculars land. Then the quadrilateral PTSU is a quadrilateral with 3 right angles, and it should be easy enough to get the fourth, right? You get the fourth right? That's what we want. Well, you don't know whether it's a right angle immediately, as no theorem or postulate directly applies. In fact, the best that neutral geometry can do is show that the fourth angle is not obtuse. You still can't eliminate the acute case. You can give this a try too. Try finding a way to prove that the fourth angle is right. If you do find a way to prove it, then either you did something wrong or you used something either directly or indirectly that is equivalent to Euclidean parallel postulate. Frustrated yet? So, what's a mathematician in the early days of the Age of Enlightenment to do? Play devil's advocate. Another way to prove that the Euclidean parallel postulate is true is to prove that its negation is false. As a reminder, the Euclidean parallel postulate states that for every line L and every point P not on L, there exists a unique line M such that P is on M and M is parallel to L. Now keep in mind that in neutral geometry, there's always at least one such parallel line. Then in the context of neutral geometry, the negation of the Euclidean parallel postulate says that there's at least one place in the entire geometry that doesn't behave like Euclidean parallelism. That is, there's at least one line L and one point P off that line where there's at least 2 parallel lines through P. Or in other words, there's at least one place in the entire system that behaves with hyperbolic parallelism. The goal then here is to prove this statement false. Now, one way to do that is to assume that it's true and then show that that assumption logically leads to a contradiction. Then the assumption must be false because contradictions are illogical.
Illogical! Illogical! Illogical!
And that's how you play devil's advocate with it. Now, if we are assuming that the Euclidean parallel postulate is false, then we are also assuming that all the statements that are equivalent to it are also false. For example, under this assumption, we also assume that Euclid's fifth postulate is false, that the sum of the angle measures of a triangle is never 180 degrees. In fact, it must be strictly less than 180. And of course, there are no rectangles. That's right, we're assuming that you can't draw a rectangle. Curiously, the first thing that you can prove from assuming the negation of the Euclidean parallel postulate is that the hyperbolic parallel postulate is true. That is, if you can find a single instance of hyperbolic parallelism somewhere in the system, then the entire system has hyperbolic parallelism. This is called the universal hyperbolic theorem, and it basically says that in neutral geometry there are only 2 possibilities. Either the geometry satisfies Euclidean parallelism everywhere, or it satisfies hyperbolic parallelism everywhere. Thus, we eliminated any possibility of some kind of mixed parallelism case. Hey, we're making good progress and it's only been 2,000 years since Euclid. But now we need to go looking for a contradiction. Well, mathematicians tried for a while. They found lots of theorems that follow as consequences of the hyperbolic parallel postulate, but no contradictions. Of course, the lack of finding a contradiction doesn't mean that there isn't one somewhere. It just means you haven't found one yet. And it seemed for a while that we would be destined to look for a contradiction for a long time. But then the story suddenly came to a close about 100 years later when world-famous mathematicians such as Nikolai Lobachevsky, Janos Boyer, Carl Friedrich Gauss, Eugenio Beltrami, Felix Klein, and Bernard Riemann finally settled the question of whether Euclid's fifth postulate could be proved from the first four. To understand how they did it, we have to discuss one last idea from an axiomatic system. An important but more subtle part of an axiomatic system is the notion of undefined terms. The axioms of a space might apply in more than one real-life context. For example, if I have two sheets of paper, then I can correctly claim that if I extend them infinitely, they both satisfy Euclidean geometry. But they have two completely different sets of lines. The lines used in the Euclidean geometry of this plane are not the same as the lines used in the Euclidean geometry of this plane. And what if there's another context somewhere else with a different set of things that I call lines that also happen to satisfy all of Euclid's axioms? Wouldn't that also be an example of Euclidean geometry? See, some of the terms in an axiomatic system are used as sort of floating terms or almost like variables. They're the fundamental building blocks of the system, and we assume that they follow the rules or axioms. But they remain completely abstract notions as we prove things about them. Only when we give them a definition can we find an example of that axiomatic system. So when I say that the lines that I want to talk about are the ones on this piece of paper, I am talking about one example of Euclidean geometry. But when I say the lines that I want to consider are on this piece of paper, I'm talking about a distinctly different example of Euclidean geometry. The only thing that changed was how I defined the line. There are two terms here that will help us later. Suppose we have an axiomatic system with some list of undefined terms. If we identify definitions of those undefined terms, like saying that the word line means the lines on this piece of paper, or something ridiculous like line means any table in this room, we call such an identification an interpretation of that axiomatic system. If it turns out that the interpretation actually satisfies the axioms, then we call that interpretation a model of that axiomatic system. So defining line as the lines on this piece of paper or as the tables in this room are both interpretations of Euclidean geometry, but of the two, only this piece of paper extended indefinitely is a model of Euclidean geometry because only its lines satisfy Euclid's axioms. The tables in this room definitely don't. In neutral geometry, and hence in both Euclidean and hyperbolic geometry, we actually have several undefined terms. The terms point, line, distance, and angle measure are all undefined. To have an interpretation, we would have to tell you what each of these terms mean. And to show that that interpretation is a model, we would have to show that those definitions satisfy the neutral geometry axioms. That is, it satisfies all the ground rules of that system. I guess you could say that the only way to make it in the axiomatic modeling business is to play by the rules. What? That one's not even funny. Yeah, I thought that joke kind of crashed and burned on the runway too. Oh. Anyway, the amazing thing about all this is that if you find a model of an axiomatic system, then that axiomatic system occurs in nature and hence naturally must be logically consistent. Well, what all these 19th century mathematicians did to settle the question of the necessity of Euclid's fifth postulate was find multiple models of hyperbolic geometry. One such model is called the Poincaré disk, discovered by Eugenio Beltrami and rediscovered and made famous by Henri Poincaré. In this model, the term point is defined as a point in the interior of the unit circle in the xy plane. The term line is defined as any diameter of the unit circle or any circle that intersects the unit circle at right angles. And in both cases, only the portion of each circle or diameter that is in the interior of the unit circle is considered a line. Angle measure is the usual angle measure in the xy plane, but distance is this weird logarithmic measure that's built out of the regular distance measures in the xy plane. Notice that this weird distance measure makes every line infinitely long, and so the edge of the unit circle represents the points at infinity. Now so far, that's just an interpretation of hyperbolic geometry. To be a model, it has to satisfy all the axioms of hyperbolic geometry. Well, it turns out the axioms of hyperbolic geometry are all satisfied in this interpretation. And hence this disk is a model of hyperbolic geometry. In particular, the first four of Euclid's postulates hold. There's a unique line between any two points. Any line can be extended infinitely, which in this case simply means to the edge of the unit circle. Circles of any center or radius can be drawn and are just defined as all the points exactly a distance equal to the radius away from that point. Curiously, circles in the Poincaré disk hyperbolic geometry model are also Euclidean circles, but their Poincaré disk center and radius are different from that circle's Euclidean center and radius. All right angles are congruent because angles are measured the same way as in the xy plane. But as we can see here, Euclid's fifth postulate fails, as we can have parallel lines that are cut by a transversal in a way that the angles on one side add to less than 180 degrees. And since they're parallel, They won't intersect on that side. In fact, all the weird stuff we expect to be true in hyperbolic geometry works here. The sum of the angle measures of a triangle is never 180 degrees. In fact, it must be strictly less than 180. And of course, there's no rectangles. So the summit angles of secary quadrilaterals are acute, as is the fourth angle in a Lambert quadrilateral. Because of models like this, we finally settled the debate, and indeed Euclid's fifth postulate must be assumed as an axiom, along with his first four postulates, if we want to guarantee that we get Euclidean geometry as a result. Amazingly, this question took more than 2,000 years to finally answer. But what's even more interesting in this story is that because of this exploration and wonder, we discovered an entirely new and completely consistent form of non-Euclidean geometry. The ramifications of this discovery didn't end there either. Bernhard Riemann, a student of Gauss and who also presented models of hyperbolic geometry, was no doubt influenced by the discovery of hyperbolic geometry in his development of the field of Riemannian geometry, which produced a completely different way of viewing various kinds of geometry using a mathematical system called a manifold with a metric on it. This introduced a more complete notion of curvature and how to do calculus on such a curved space. And this gave us ways to describe more precisely the geometry of things like spheres and hyperbolic paraboloids. The field of semi-Riemannian geometry developed not long after due to the influence of people like Hendrik Lorentz, Hermann Minkowski, and others. Semi-Riemannian geometry provided the mathematical framework necessary for Albert Einstein to extend special relativity to general relativity. Thus, in a roundabout way, this exploration of Euclidean geometry and the question of the necessity of Euclid's fifth postulate set off a chain of mathematical discoveries that eventually led to one brilliant person at the right point in history to be able to revolutionize the way that we understand gravity and the universe as a whole. Up until these last few minutes, you would not have been faulted for thinking that everything we talked about today was just an exercise of pure mathematical interest. But nothing in mathematics is so isolated. Mathematical research of any kind deepens our understanding of truth and influences our views of the world around us. In this box from my garage, we started with a geometry that was intended by Euclid to describe much of the world around me. And we followed that line of thought to discover purely abstract ideas of geometry, but eventually came back to realize that some of these abstract ideas are not so abstract after all. With the discovery of general relativity, we not only know more about how the universe works on large scales, but it also is critically important to understand in order to make things like GPS satellites work, a topic for another time. But now every time you ask Google or Siri for directions, you're using mathematics that was developed and influenced by a burning mathematical question that took over 2 millennia to answer. Well, I hope that you enjoyed this exploration of Euclid's fifth postulate and the development of geometry. This video is made in part of a celebration of this channel recently passing 500 subscribers. We want to continue to grow, and so if you enjoyed this video, give it a like and subscribe to Scholar Sauce, and please share our content with your friends. The more support we get, the more frequently we can produce videos like this one. If you're interested in exploring more of how geometry influenced the development of general relativity, or simply want to know what general relativity even is, check out this video here of an introduction to general relativity using just pictures. You can also check out this video where we explore the geometry of a sphere and find triangles that have angle sums bigger than 180 degrees. Thanks for joining us, and we'll see you next time on Scholar Talk.